Hello, my name is Marta Yebra, and in this short video from the Vegetation Remote Sensing video series, I'm going to give you some examples on the use of remote sensing to map land cover or vegetation distribution on the ground and biodiversity. Traditional classification of vegetation by remote sensing has entailed the visual interpretation of aerial photographs. Recognition of target is the key to interpretation and information extraction. Observing the difference between targets and their backgrounds involves comparing different targets based on any of all of the visual elements that you may have heard of. These are tone, shape, size, pattern, texture, shadows, and association. Visual interpretation using these elements is often a part of our daily lives, whether or not we are conscious about it. You may have already worked it out what is this in this slide using these visual elements, but if not, here you have the answer. It's a fruit tree orchard in Spain. The focus of vegetation detecting by remote sensing have shifted to the interpretation of satellite imagery. Approaches to classification are generally referred to as supervised or unsupervised, but this material has been already explained in the video series about interpretation remote sensing data, so I'm not going to go into details here. However, I would like to reiterate that image classification is possible because different elements of the landscape present different spectral responses. But even a same element or similar vegetation type, like for example crops, that have similar spectral curve with a significant minimum of reflectance in the visible portion of the spectrum and a maximum in the near infrared, have slight differences in the shape of the reflectance spectrum that are evident enough to be used to the identification of different crops, as you can see, for example, in the results of the classification of a various image of irrigated crops in San Luis Valley in United States. The same applies to different tree or shrub species. Again, these species present similar spectral curve, but slight differences in the shape of the spectra that can be used for the identification of vegetation types. This is the base for mapping biodiversity and species distribution, for example. There are now new approaches that integrate these spectral remote sensing methods that I have just mentioned with phylogenetics and chemical composition, and this is collectively called spectronomics. This slide shows an example of the organization of tropical plants based on these principles. Note that the differences in its leaf constituents contribute to the uniqueness of its species chemical fingerprint. So the Carnier Institute of Stanford University is being used in a very high fidelity imaging spectrometer to map biodiversity based on this concept. And here you have a picture of the airborne aircraft and one of the sensors mounted on it. This is specifically the very high fidelity visible shortwave infrared spectrometer that measure in the range of 380 to 20, well, from the visible to the shortwave infrared wavelengths. And also this institute have a dual laser waveform LiDAR system and a high resolution visible to near infrared imaging spectrometer. So using the concept of spectronomics and the platform that I have just shown you, they can map biodiversity following this methodology. So the LiDAR, well, first, of course, they fly over a rainforest site, and then the LiDAR provides guidance for the spectronomic sampling of rainforest canopies, but also controls the three-dimensional architecture of the plants and the solar and the sensor viewing angles. In this step, the LiDAR is used to extract the best spectra from the canopy of the trees, and that can be compared with the different trees in the neighborhoods. The spectra selected are compiled at a high spatial resolution in an image format, along with the canopy structure data from the LiDAR that allows for automatically get information about the crown, shades, and another non-canopy surface. The selected canopy spectra are reduced to equivalent leaf spectra using radiative transfer modeling version methods, following by one algorithm that calculates the spectral diversity of a specific spatial resolution. In this map in red, you can see areas where the spectral diversity is high, and in green areas where the spectral diversity is low. So the spectral diversity is converted to plant species richness using statistical methods. Then the spectral signatures are also converted to the chemical fingerprints using regression analysis. And together, the spectra and the chemical are used to search a database for potential matches at functional group, family, genus, and potentially species level. Finally, an additional detections are carried out at different taxonomic scales to identify particular species of interest, as you can see here in red. In this slide, I show an example of a hyperspectral cluster analysis of the rainforest species based on their reflected light from the visible to the shortwave infrared. The color codes show the spectral signatures of each species, with yellows and reds showing high and greens and blue showing low reflectance. The dendrogram to the right shows the phylogenetic clustering of the different species. To finish with this video, I'm going to present the National Dynamic Land Cover Dataset of Australia that Geoscience Australia has derived using vegetation classification techniques based on time series or EVI from Moody's and different dynamics of vegetation. The time series includes hundreds of snapshots of vegetation greenness for each pixel of its Moody's pixel area across the continent over more than 8 years period. Here you can see an example here on the top of the time series display for a closed forest in red and a irrigated gramineous in blue. The EVA time series for its Moody's pixel area was characterized using 12 time series coefficients which describe the statistical, phenological, and seasonal characteristics of the land cover. And then a clustering approach again was applied to these 12 coefficients to define homogeneous regions with similar greenness dynamics over time. Regions that show similar greenness characteristics over time were assigned to the same land cover category. So in this slide, I show an example of the phenology or changes over time of a crop area. The green fractional cover, as you can see, raised sharply as the crops mature and then remains high for a little time before a sharp drop in the green fractional cover after the crop is harvested. There is then an interval of zero greenness here, which follows the fallow period. So time series analysis of the cropping phenology can identify a range of features. For example, the number of cropping cycles within a year, also the number of cumulative time of fallow periods, or the timing of crop cycles, whether these cycles happen in summer or winter, for example, and also the area under this curve that represents the crop green biomass. And of course, interannual changes in crop green biomass can be also observed with these graphs. In addition to the land cover map, this product from Geoscience Australia also contains 3 layers that show the trend in annual greenness characteristics over time. This trend layer highlights areas that are becoming greener or less green over time. As an example, here you can see the trend of EVI, and the trend was calculated as the slope of the line for a linear regression of the annual EVI mean values. So the trend data can be used to identify, for example, areas where the vegetation is showing internal annual changes over time. And as I previously mentioned, it is important to know that the trend data play a valuable role in detecting change. However, additional data is required to identify which is the driver of that change in greenness. For example, an increase in greenness may represent an increase in the presence of invasive weeds rather than an improvement in productivity or condition. And just to finish this short video, I just leave here some other examples of global vegetation maps in case you want to explore them for your use in your projects of this course.